Hello, dear students. I welcome you all on behalf of Sri Jayendra Rank Zone classes. In the previous lectures of wave optics, we have seen the polarization of light, Young's double slit experiment, and the fringe width of bright and dark fringes. Now, in this lecture, we are going to study the diffraction of light. So, let us begin. Let us take a light source in front of which there is the obstacle. On the screen, the shadow experienced or shadow observed is the geometrical shadow. This much portion is illuminated and this portion will be dark. Now, in second situation, we have kept two obstacles and light is passing between these two obstacles. In this situation, the mid portion will be illuminated and the rest of the portion will be shadowed. So, the diffraction is defined as the bending of light near the edges and corners of an obstacle or slit and spreading into the region of geometrical shadow. Is known as diffraction of light. So basically, bending of light from a corner is called diffraction of light. Now, there are two types of diffraction. One is Fraunhofer diffraction. There we can say two experiments regarding the diffraction. One is Fraunhofer diffraction and the other one is the Fresnel's diffraction. In the Fraunhofer diffraction, the source of light and the screen on which the diffraction pattern is obtained are effectively at infinite distance from the diffracting system. In this case, diffraction pattern is obtained by using convex lens, and the pattern is obtained using convex lens. So the source and screen are at infinite distance and we will use convex lens. As the source is at infinite distance, we will consider plane wavefront in this case. The second is Fresnel's diffraction. In this diffraction, the source of light and screen are kept at finite distance from the diffracting system. As the source is at finite distance, we will consider cylindrical or spherical wavefronts depending on the type of source. If source is point-sized, then there will be spherical wavefronts, and if source is linear, then we will consider the cylindrical wavefronts. First, let us see the Fraunhofer diffraction or Fraunhofer's single slit experiment for diffraction. Here, in Fraunhofer's experiment, the source is at infinity. So light rays are coming from infinity. To focus them, we are using a convex lens. So light is focused at a point. The light is passed from the slit, then from the corners of the slit, light will bend at an angle theta, and some light will bend at an angle theta, and they will focus at another point on screen. In this case, the diffraction pattern has three fringes, or it consists of one central maxima, central large maxima. This is central maxima. Second, alternate maxima and minima. Above and below central maxima, we will have alternate maxima and minima. And in this situation, unlike the double slit experiment, the entire pattern is not steady state, it's very complex with less contrast. Your visibility is not one. Now let us see how the intensity of light varies in single slit diffraction. We have drawn a graph of intensity of light versus wavelength. Here the intensity is maximum, so this is central maxima, and then with different wavelengths, this is first maxima, this is second maxima, third maxima, and so on. Let us take the case 1, in which if S is equals to D, this means the separation between central maxima of two objects is just equal to the distance between the central maximum and the first minimum of any two objects is equal to the distance between central maximum and first minimum. In this case, two objects are said to be just resolved. Let us take the case 2. In this situation, if S is greater than D, that means separation between central maxima of two objects is greater than the distance between the central maximum and first minimum. In this case, two objects are said to be well resolved. Objects are well resolved. Case 3. If S is less than D, that means the separation between the central maxima of two objects is less than the distance between the central maxima and first minimum. In this case, the objects are said to be unresolved. So the patterns are not clear. Let us understand the Rayleigh's criteria. It states that the image of 2-point objects close to each other are regarded as just separated if the central maxima of one diffraction pattern falls on the first minimum of the other diffraction pattern. Let us distinguish between the interference and diffraction. In both the cases, the light and dark pattern occurs, but there is basic difference between interference and diffraction. So let us note that down. First, in interference, the cause of interference is the superposition of waves takes place to form bright and dark bands, wherein diffraction, the superposition of waves takes place to form maxima, region of maximum intensity, and minima, the regions of minimum intensity. Here, all the bright bands have same intensity, wherein the diffraction pattern, the central bright has maximum intensity and as we move away from the center, the intensity of maxima goes on decreasing. In interference, the size of every fringe is same, wherein diffraction, the size of central maxima is larger than other maxima. All other maximas will have same width, but central is larger. The resolving power of an instrument that works on interference of light. Does not depend on the phenomena of interference, but in diffraction, the resolving power of optical instrument depends on the diffraction. Let us understand what is resolving power. When two objects and their images are very close to each other, they appear as one, and it may not be possible for the eye to see them as distinct objects. Let's say there are two objects which are placed very close to each other. We may not be able to separate them. If the objects are not seen separately, then we say that details are not resolved by the eye. Then the optical instruments are used to assist the eye in resolving the objects or images. So basically, resolving power of any object or eye is the ability of eye or any optical instrument to view it separately, to view two objects separately. If they are not seen separately, when placed close to each other, they are not properly resolved. So we need to use some optical instrument for the assistance. The method adapted to see the close object as separate object is called resolution. It is the method to see the objects as separate objects is called the resolution. The ability of an optical instrument to produce distinctly separate images of two objects located very close to each other is called resolving power. But we use resolving power in two different terms. In terms of microscope, in terms of microscope and telescopes, we talk of geometrical resolution. Where the geometrical positions between the two nearby objects are to be resolved. But in case of spectroscopes, here geometrical positions are to be resolved, where in case of spectroscope, we refer to spectral resolution. This refer to spectral resolution, where differences of wavelength of light in a given source are to be resolved. Resolving power is normally defined as the reciprocal of the smallest angle subtended at the objective of optical instrument by 2 point objects, which can be just distinguished as separated. Now, what are the limit of resolution? Every device or every human eye has some limit for resolution, that is called limit of resolution, denoted by D. It is the minimum separation from each other of two objects, so that their images are images which are produced by microscope are just seen separate. That means if the distance between the two objects is lesser than this limit of resolution, then given device is not able to produce separate images. This is called limit of resolution. The resolving power can be written as 1 upon limit of resolution D. Now let us understand the resolving power of microscope. The least distance between two just resolvable objects point is given by limit of resolution, and that is equal to 1.22 lambda divided by 2 mu sine theta. Here mu is the refractive index of medium in which objects are placed. Here, make this thing clear. It is not the refractive index of material of lens. It is the refractive index of medium in which objects are placed. And theta is the semi-vertical angle or half angle subtended by lens at the objects, and lambda is the average wavelength. If this is the lens, an object is kept at point O in medium of refractive index mu, then the angle subtended by lens at object is, let's say total angle is 2 theta, then half angle is theta. Here the resolving power is 1 upon limit of resolution 1 upon d, that will give us 2 mu sine theta divided by 1.22 lambda. Let us see the resolving power of telescope. Here d is the diameter of the objective which will enter to our pupil. The magnifying power of a telescope is given by m is equals to capital D by small d, and small d is the diameter of exit pupil. Capital D is the diameter of entrance of pupil, and small d is the diameter of here. The magnification of a telescope is said to be normal of d. The diameter of the exit pupil is equal to dE and the diameter of the eye. So d is equal to dE. So the normal magnification is given by capital D upon small de. Further, the limit of resolution of telescope is given by d theta is equal to 1.22 lambda by capital D, and the limit of resolution of I is given by d theta is equals to 1.22 lambda upon dE. From this equation, we can write d theta dash upon d theta is equal to limit of resolution of I to the limit of resolution of telescope, that is 1.22 lambda divided by dE whole divided by 1.22 lambda divided by capital D, D upon dE, that is magnifying power. So the product of normal magnifying power of telescope and its limit of resolution is equal to the resolution of unaided eye. This is all for today. Thank you.